So this is G485 homework booklet question 7. We've got a setup you've seen before with some magnets in a yoke sitting on a scale. This scale very handily is giving us a force directly in newtons. We've got a circuit set up, and the point is that the rod is held still. And the first thing, perhaps unsurprisingly, we're going to be asked about is the direction and how we determine it. Well, how we determine it for a 1-mark question, we can always simply get away with stating by Fleming's left-hand rule. The direction of the force, then we need to then apply Fleming's left-hand rule to this situation where I've got a field in that direction, so you need your first finger of your left hand pointing in that direction. I've got a current coming from the positive side of the cell to the negative, so the current's flowing around that way, so in the region that matters the current is flowing there. So I've got a second finger running that way, first finger pointing that way. If you do that with your left hand, you end up with a thumb that's pointing down. So that's the answer to part A. It's going to be a downward force. Part C, straightforward use of F equals Bill. Everything's at 90 degrees, so we don't need to worry about theta at all here. The one thing I have highlighted is you are told specifically the length of the rod in the field. They could have been meaner and given you the overall length of the rod and the length of the magnetic field, and it would be the length of the field if that was the case, because it's L in F equals Bill is the length of the rod in the field at 90 degrees to that field. So just be aware of that. But here it's straightforward, 5 centimeters, put it in, and we get 0.016 newtons. Then we've got to state and explain the new reading on the balance. Again, we need to look at the diagram, think carefully about what's going on here. We're told that, or we've worked out, sorry, that the rod is being pushed downwards. Now that's due to an interaction with the magnets, with the magnetic field due to the magnets. So if the rod itself is pushed downwards, by Newton's third law, if the magnets essentially are pushing the rod downward, then the rods must push the magnets upwards. So this reading on the scale there is going to go down. So hence take you back to the calculation I've done, the 2.500 minus 0.016 minus that, because it's going upwards as opposed to the weight that was downwards, so I'm getting 2.484, and I've given you those reasons. The force on the magnets is upwards because due to Newton's third law, the forces on the rod and the magnets are equal and opposite. So we've now got a, having done that bit of work, which is very much a bit of G484 synoptic work, we've got a little bit that's G482, thinking about resistivity. We haven't got any information on the original rod, so we are going to have to do this all by factors and by the amount of changes. We halve the diameter of the original rod, and that's going to mean that the area is going to decrease by a factor of 4 pi r squared. So halving the diameter is going to take us down to a quarter of the area, and that's going to mean the resistance will increase by a factor of 4. R is rho L divided by A from G484, so by halving the diameter, I decrease by a factor of 4 the cross-sectional area, which means I increase the resistance by a factor of 4. Just from V equals IR, if I've got 4 times, as you can see here, if I've got 4 times the resistance, I'm going to have a quarter of the current, so the current's going to decrease by a factor of 4, and because of the force being Bill, if the current has decreased by a factor of 4, that means the force has decreased by a factor of 4, taking me down to that final value of 0.004. So that is G485 homework booklet question 7.